So we have seen this. So real gases at a low temperature and a high pressure, the liquefaction begins. And after the gas has become liquid, no appreciable further change, further volume change. Similarly, in isotherm also at high pressure liquefaction begins and no further volume change was observed. And in the next slide, we are going to discuss, look here, this is a very qualitative understanding of the ideal gas. I am taking a container of volume V in which I am having n moles of the gas and I am measuring the pressure here. Experimentally, I measure the pressure. And what is the pressure inside the container can be calculated using the ideal gas equation. P theoretical is equal to nRT by V because PV is equal to nRT. So P theoretical into volume is equal to nRT. Therefore, I have taken the volume that side. Therefore, the theoretical P can be calculated like this. For an ideal gas, this experimental value and the theoretical value will be equal. So if you take the experimental pressure along y-axis and the theoretical pressure along x-axis, you will be getting a straight line like this. So when the theoretical pressure is 1 atmosphere, experimental pressure will also be 1 atmosphere. When the theoretical pressure is 2 atmosphere, experimental pressure will also be 2 atmosphere. Therefore, there is linear change, or they are almost equal. They are equal, not almost, they are equal. But in the case of real gases, what happens? If you take the experimental value and the theoretical value calculated using the ideal gas equation, so please, all of you, mute your mic. Some disturbance is coming. Stella. So when you take a real gas, the experimental and the theoretical, the ideal gas line is this, but real gas lines will be getting deviated from the ideal gas line like this. So this is because of the intermolecular forces. That is why the effective pressure of a real gas is called a fugacity. Pressure plus or minus internal pressure is equal to effective pressure. So this internal pressure arises due to intermolecular interaction. Suppose if you want to understand this, I can tell you like this. Suppose many of you were hostelers. Suppose you are having a hostel where 4 people can be accommodated in a room. If these 4 people are neither friends nor enemies, so they will be experiencing a space crunch or space management, and they will experience a pressure. So that is ideal pressure. Let me say, what is theoretically expected will be practically found. Suppose if these 4 people are enemies, so their interpersonal repulsion will be more. The 4 people are asked to stay in a room where these 4 people are enemies, means the pressure that they are experiencing will be more than what is expected because of the interpersonal repulsion. If these 4 people are very close friends, if they are allowed to stay in a place where only 4 people can be accommodated, the pressure that they are going to experience will be less than what it is calculated for normal people because of the interpersonal attraction. Therefore, the normal calculated pressure according to ideal gas equation, plus or minus internal pressure which is developing due to the intermolecular interactions. If it is attraction, then that has to be subtracted. If it is repulsion, then that has to be added. And the addition or subtraction of the internal pressure which arises due to the intermolecular interaction with the normal pressure calculated for that volume, that temperature, and that number of moles using the ideal gas equation will be equal to the effective pressure. That effective pressure is called the fugacity. Fugacity is effective pressure. And how to calculate the fugacity, how experimentally the fugacity is determined, these are all the things which are found in the textbooks in gaseous states. But for your syllabus, this is of not much interest, and therefore uh, this much of understanding is sufficient regarding the characteristics of an ideal gas. So once again, I would like to repeat what we have seen in the gaseous state so far. So we have seen the differences among the solid state, liquid state, and the gaseous state, and according to the thermodynamic things and also the translational, vibrational, rotational motions, and we differentiated them. And then we have seen why gases behave in a peculiar manner. It is due to the negligible attractive force and also the large wide spaces among the gas molecules. And we have seen the Avogadro's law, Boyle's law, and Charles' law. And we have also discussed the nature of the universal gas constant R. And at this juncture, I would like to tell you one more thing. Actually, universal gas constant is 8.314 joule per Kelvin per mole. A scientist calculated the same constant for a molecule by dividing R by Avogadro number. When you divide R by Avogadro number, you will be getting a constant per molecule, that is joule per Kelvin per molecule, which is called Boltzmann's constant, K. Nk is equal to R, or K is equal to R by N, where N is the Avogadro number. So it was calculated by the scientist Boltzmann. Hence it is called the Boltzmann's constant, which is of high importance in thermodynamic calculations. Boltzmann's constant. So this R can be expressed in different units: joule per Kelvin per mole, calorie per Kelvin per mole, liter atmosphere, that is pressure into volume. Pressure into volume itself is work unit, pressure into volume. And the same thing can be expressed in millimeter of mercury into liter also. So there are 4 different ways by which the R can be expressed. And also we have seen what is a normal pressure, normal temperature, and molar volume also we have seen. It is 22.4 decimeter cube or 22.4 liter or 22.4 into 10 power minus 3 meter cube. And we have seen what is an ideal gas in the view of thermodynamics, in the view of a gaseous state, and also in the view of intermolecular forces. We have seen what is an ideal gas, and we have seen the graphical representations of Robert Boyle, Charles, and Gay-Lussac, and we have derived an equation for the ideal gas, and we have proved that ideal gas equation holds good as long as intermolecular forces are not there. If intermolecular forces are there, then the pressure calculated using the ideal gas equation and the experimental pressure calculated will have a vast difference. That is why the pressure of a real gas is called fugacity, which is called the effective pressure. And in this derivation, on the basis of this derivation, we have calculated the universal gas constant R, and it comes to the same value, 8.314 Pascal meter cube per Kelvin per mole. So it is also 8.314 joule per Kelvin per mole. And we have we have discussed the intensive and extensive properties, and in a different approach for the gaseous state and in the thermodynamic state. And we have seen isotherms, isobar, and isometric. And from isotherm, isobar, and isometric, we have discussed that ideal gas whose volume is 0 at 0 Kelvin, and also volume approaches a 0 value when the pressure approaches infinity, and also the real gas at a low temperature and high pressure, it gets liquefied, and after liquefaction there is no appreciable change in the volume. And in the isotherm at high pressure also it gets liquefied, and after liquefaction there is no appreciable volume change. Therefore, ideal gases do not have intermolecular forces, and real gases have intermolecular forces. And this is uh, a qualitative comparative study of ideal gases and real gases. And when you calculate the pressure according to ideal gas equation, the calculated pressure and the experimental pressure for ideal gas, they are equal. But in the case of real gas, it is different. So real gases have some internal pressure which arise due to the intermolecular interactions. So with this, we come to the end of today's discussion. So let us see in the next class.